I just noticed some of the videos they do not have the sound, so I'm just doing the cover part. So this video is talking about section 3.2 is talking about trigonometry integral. Just in these sections, we will use some of the identities from trigonometries. We have the Pythagorean identity sine squared x plus cosine squared x equal to 1, which can be rewriting as cosine squared x equal to 1 minus sine squared x, sine squared x equal to 1 minus cosine squared x. We also have the double angle or the half angle formula. Sine square x equals to 1 minus cosine of 2x over 2, or 1 half minus 1 half cosine of 2x. Cosine square x equal to 1 plus cosine of 2x over 2 equals to 1 half plus 1 half cosine of 2x. Now let's looking at some examples. We have integral of sine to the fourth power of x, cosine of x dx. So this is different than the traditional antiderivative of sine or antiderivative of cosine. So for those, we will definitely using u substitution to find it. Where cosine of x, we know the antiderivative of cosine x and then the derivative of cosine x is the sine or cosine. So we can let u be equal to the sine of x, where the derivative of the u is cosine of x, which is matched to the one's cosine x dx. So we can rewrite as integral of u to the fourth power du, which is easy to find the antiderivative. We got u to the fifth power over 5. Replace the u with sine of x. We got sine to the fifth power over 5 plus the constant c. So we actually spot the cosine of x dx first, so we know that this is going to be our du. In this version, to find the u, which is sine of x. So another example. We want to find the integral of cosine cube x times sine square x dx. So you can see this one is different than the previous one. The previous one, we have cosine of x dx. We can just this one tell me we are going to use in the u substitution. But here we do not have sine of x dx or cosine of x dx. We have both cosine in the third power, sine in the second power. So for this one, we were using the identities, Pythagorean identity in particularly. We're going to rewrite sine squared x in terms of 1 minus cosine squared x. And we can multiply it. I think a lot of time when we're trying to do antiderivative, there's a lot of trial and errors. So even though this is the first idea I have, but once you figure out, you will see that it is a little bit hard to find the antiderivative. So we want to match to the previous example. So let's rewrite the cosine cube x in terms of one copy of cosine x and then two copies of cosine x. So cosine square x times one copy of cosine x times sine square x dx. Where the cosine x dx, that gives us the du, like the previous one. So du equal to cosine x dx, so u is going to be sine of x. Then since u is sine of x, we need to rewrite cosine square x in terms of 1 minus sine square. And cosine x dx will be replaced as du. So after the u substitution, we will get 1 minus u squared times u squared du. Now we can multiply everything. And using the power rule to find the antiderivative, which is going to be u to the cube over 3 minus u to the 5th over 5. Replace u back to the sine. So we got sine cube x over 3 minus sine to the 5th power over 5 plus the constant c. So from those two examples, that tells us that when we have odd powers in the cosine of x, we can always put out a cosine x dx, and using the u substitution, u equal to sine of x, du equal to cosine x dx, to find the antiderivative. When we have cosine in the even power, we cannot use the u substitution. We cannot use the Pythagorean theorem to rewrite as 1 minus sine squared because it's not really helping us. So we're going to using the double angle formulas, which is cosine square x equal to 1 plus cosine of 2x over 2. Or 1/2 plus 1/2 cosine of 2x. Where the antiderivative of 1/2 is easy, is just 1/2 x. But for cosine of 2x, we have to use the u substitution. So when u equal to 2x, then du is just equal to 2 dx. In other words, dx is equal to 1/2 du. Then let's just looking at cosine of 2x dx. This one can be rewritten now in terms of cosine of u times 1/2 du. We can put a 1/2 out, where the antiderivative of cosine of u is just equals to sine of u. And once we replace u back to 2x, this one becomes to 1/2 x from the 1/2 at the beginning, plus the 1/2 from the original purple one, multiply by the red 1/2 from the antiderivative of cosine 2x, which is 1/2 sine of 2x. So combining everything, we got x over 2 plus sine 2x over 4 plus c. So that means when we have an even power for the cosine function, we will use the double angle formula. So let's move on to another example. We have cosine of ax sine to the cosine to the 8th power sine to the 5th power and dx. So for this one, it's kind of similar to the previous one. We have an even power for the cosine, so we're going to using the half angle formula. But we still need to deal with the sine to the 5th power. So we can split sine to the 5th power in terms of sine to the 4th power times sine x dx, where sine x dx tells me that I'm going to using the u sub for u equals to cosine of x, where du is equals to negative sine of x. And then next, we need to rewrite sine to the 4th power in terms of cosine. So sine to the 4th power, that is sine square. So sine square is 1 minus cosine square. So sine to the 4th power is 1 minus cosine square, the quantity square. So now we can use the u sub to replace cosine of x as a u. Now we need to multiply the 1 minus u square quantity square. FOIL it. We got 1 minus 2u square plus u to the 4th power. And then distribute the u to the 8th power. Using the power rule, we got u to the 9th power over 9 minus 2 times u to the 11th power over 11 plus u to the 13th power over 13. But we're not looking for u, we want x. So we're going to rewrite u back. We got negative cosine to the 9th power over 9 plus 2 cosine to the 11th power over 11 minus cosine to the 13th power over 13 plus c.